Okay, well, let's get started then. So in today's lecture, this is a final lecture of the Computer Science 212. We'll be covering, this will be similar to last time, we'll be covering a problem that overall we may understand, but we'll be covering a little bit deeper than that. And again, it's a kind of a standalone lecture too, so you don't necessarily need a lot of background to do that. If you understand the general material, the data structures, etc., we should all be okay. Okay, so let's get started. The focus of the lecture will only be on the minimum spanning tree. That's a problem that we have covered earlier. So some of it should be familiar, but we'll be going in a little bit deeper than that. It's also a little bit of overflow. The points that we didn't have a chance to make earlier during the lecture, we can make them now. We can go a little deeper. Okay, so this is the rough agenda. We'll just talk about the problem a little bit, talk about the algorithms, the data structures, the finesse, talk about a little variations here. So essentially, this is a problem that's given to us in a direct sense. We have these houses and there's a central office and we would like to connect them with the wires, and there's a cost of going from here to here, here to here, and we would like to minimize our cost. Or perhaps do something else. So based on what we would like to do, our solution is going to be different. So one solution could be this approach. We connect all the houses to this central office. And the note is that it's expensive because then you are connecting many different wires. The cost of the wiring is going to be high. So the other approach is that we could connect them like this, and if we can use this wire to both do whatever the data transmission is going to happen from this to this node or from all the way, then we can do this connection using much cheaper. So again, these are the two options. So it depends upon what you're trying to solve. Either the cost is that high or you're trying to do something else. Either of those solutions could be the right solution depending on what you're trying to do. So for example, when we connect the switches to the actual computers, even for example in a company setting or in an educational setting, you have many different computers that are all connected. They are actually connected this way. They are not connected this way. So for example, in this building where we might have, I don't know how many people sit here, but it's safe to assume that, let's say, more than 500. So imagine any building that has at least 500 people. So these are all the 500 rooms or cubes or all the places, and they have multiple computers. And the central office in this context would be, what would be the central office in this context? Sorry? Yes, exactly. So it would be a comm closet, right? So what closet did you refer to it as? Network closet, right? So it would be a comm closet, or it would be, so it's an area that's usually, we walk right past it, but it's not made to be very conspicuous, right? Since it's just a closet. So you might have a comm closet on each wing, on each floor, and then perhaps they connect a little further, right? So this is how usually the comm closets connect to the individual computers. Even, for example, in a particular room, there might be 3 computers or place for 3 different computers. They would be connected this way. So what is the reason that even though this says that this minimizes the total length of the wire, but this is the way that we normally use it? Not really. Not really, because you could make that to be a wire that has a higher throughput, and then that would not be that case. So there must be something else. That's the reason here. Tell me a little bit more about that.
Well, for the other one, if one of the lines were to be cut off, and all the other ones.
Exactly. So we connect. Each computer is connected, so it's not each computer, but each jack in the room, right? It's connected to the comm closet, or at least to a central place, so that if there's a problem with that, and there's frequently a problem with that, you'll say, oh, don't use that jack doesn't work. That means there's a problem with the wire. But you can connect to the other wires without any problem, other places without any problem. So depending upon what you're trying to do, this may be what you want to do, or this may be what you want to do. For example, in a small setting, in a small local area network, the cost of an RJ45 is not that expensive. It's not that high. But if you're trying to connect in a rural area some central place to all the different cable consumers, then this might be the right way to go. And based on the distance, then this would be an example of what we would call a minimum spanning tree. So this is a problem, we are familiar with it. I'll just rephrase it, just in case, just to refresh our memory. So it's a subgraph of an undirected, we are referring to undirected graphs here. It's a weighted graph, that means each edge has a weight. So we are trying to find a tree, so that means there cannot be any cycles in it, and it has to connect all the vertices. So that means we are going to have v minus 1 edges, and the total cost associated with the edges is minimum. And we recognize up front that it's not necessarily unique. So if there are edges with multiple edges with the same weight, then we are going to find multiple minimum spanning. Okay, so up to this part we are familiar with it, and even what I'm going to cover next, we are in general familiar with it. Let's just take a look at an example. So here's a graph, and we are trying to find a minimum spanning tree. Just visually inspecting it, this seems to be the right minimum spanning tree. Consider taking these edges that are weight 2, 4, 4, and 5. So this spanning tree has a weight of 8, 13, and 15, which is the minimum compared to any other edges. So this is the unique minimum spanning tree in this case, but is it necessarily? I believe it's necessarily unique, but you can inspect it a little further to argue that. But in general, a minimum spanning tree does not need to be unique. So here are the algorithms that we have covered, not all of them, but we have covered some of them at least to some extent. So one of the first algorithms, the first documented algorithm, is called the Borufska's algorithm. It was designed by a person by the name Borufka, Czech scientist, he was motivated by an actual problem. He was asked to do the electrical coverage for Moravia. I believe Moravia was a principality of Czech even at that time, and my memory of history fades me in that. But it's again, it's a region in the eastern part of Czech Republic. So he was motivated by a very practical problem, and he came up with this algorithm. But because the Czech Republic at that time was in the Eastern Bloc, this algorithm was not well known in the West at the time. And then it was rediscovered many times because it was a good algorithm, it made sense. The problem was very meaningful. It was rediscovered many times. So this was done in 1926. It was published. It was there in a journal, but nobody was referring to the journals maybe that are in Czech language or Russian language. So this algorithm was rediscovered many times between 1926 and 1950 until it was rediscovered by somebody in the West, and then it became a standard because then everybody could understand the algorithm and everybody was referring to it. Two other algorithms were also very well known, and those are the algorithms that we did cover in the class earlier, the Prim's algorithms and the Kruskal's algorithm. So let me talk a little bit more